Our equation here, y double prime plus 3y prime plus 2y equals 6, is an example of a non-homogeneous higher order equation. Specifically, our g of x here is any constant, or is a constant 6. That is very important because for non-homogeneous equations and solving for such equations, we'll be following this form. General solution of the form y is equal to y sub c plus y sub b. Unlike before, for homogeneous equations where we automatically take the version of this equation using differential operator d and then moving to auxiliary equation, then we solve for our roots, and then the general solution will be dependent on what the type of roots, whether they are real or imaginary, or whether they are repetitions. Here, we are going to use two different forms of to be combined for our general solution. The same process as mentioned earlier is actually our y sub c. That is what when we assume that our right hand side, our g of x, is equal to 0. It's not 0 here, but it's part of the process to solve for the solution here when we assume that our right hand side is equal to 0. That's for our y sub c. So still, the process involved before are very important here. Now, what about y sub b? Y sub b to be added on our y sub c is actually a particular solution when we use this type of table presented here. This table shows the different forms of y sub b depending on whatever would be our g of x. And since our g of x is a constant, let's look at number 1. We'll be using y sub b in a form of a. Later, we will not be sticking with a because we will be solving the value of a to be added to our y sub c. So first, let's solve for y sub c. The y sub c again is when we take the same process of solving homogeneous equations where our g of x is equal to 0. Hence, we will have this form with differential operator d. So you have here d squared plus 3d plus 2 times y is equal to 0. And with that, we will have our auxiliary equation. You're going to have in this form m squared plus 3m plus 2 equal to 0. Okay? So let's solve for the roots of this. We know that this is this can be factored as m plus 1 and m plus 2. If you have problems with factoring, please try to review that. We also have different videos on our channel to help you with the process. Our first root here is when we equate this to 0 according to zero factor property or zero product property. Our first root is minus 1. Then our second root, m sub 2, is negative 2. Take note that our roots here are both real and are not the same. That would mean we'll be using the general solution for our y involving distinct and real roots, but to specify that not the same as that, of course, this is just y sub c equal to this form. C sub 1 e to the power of m sub 1x plus c sub 2 e to the power of m sub 2x. We just have two terms because we only have two roots that are distinct. And simply plugging in our m sub 1 and m sub 2, I think that they can be interchanged, whichever root you will be writing first. But since I recorded m sub 1 as negative 1, so you will have c sub 1 e to the power of minus 1x plus c sub 2 e to the power of your second root minus 2x. Or you can simplify this further, so your y sub c is c sub 1 e to the power of negative x plus c sub 2 e to the power of negative 2x. This is your y sub c. Okay? This is just the first part of your solution as we still need y sub b. Now looking into this as our part of our table earlier, we have y sub b equal to a. It's not the same. It's not all the time a. It depends on what is your g of x. But since our g of x is constant, we'll have that. If it's not constant, let's say linear, quadratic, we'll have different forms as well. The hint here is this. Our highest degree of order of derivative is 2, or y double prime. Hence, we also be taking its second order derivative. But first, the first order derivative of constant a is just 0. And the second order derivative of 0 is also 0 here. So with this, we are going to substitute this on our given equation. Our equation, this is for solving y sub p, please take note of this. Our original equation is y double prime plus 3y prime plus 2y equal to 6. To solve for a, we are going to introduce a here by substituting y sub p for y prime of p for this, and y double prime of p for this here. So you will have y double prime of p plus 3y prime of p plus 2y sub p equal to 6 as well. And substituting the values presented here, your y double prime of p is 0 plus 3 times your first order derivative of y sub p is also 0 plus 2 times your y sub p is a equal to 6. Okay? So this is 0 plus 0 plus 2a equal to 6. So 2a is equal to 6. A is 3. Now that we have our value of a and we don't have other variables here, what was our y sub p earlier? Based on our table, our y sub p is just equal to a, and since a is equal to 3, y sub p is just equal to 3 as well. So we have y sub p now. Earlier, we have solved y sub c. So for our general solution, which is the sum of both, we simply structured them in this manner. So our solution is y is equal to y sub c plus y sub p. Y being y sub c here, c sub 1, e to the power of minus x, plus c sub 2, e to the power of minus 2x. That was the solution here. Plus your y sub p, which is just equal to 3. This is now the solution of the given higher order non-homogeneous equation. Again, we solve for y sub c, then we solve for y sub p, but then again, please be guided that it's not a all the time. It depends on the situation of our g of x. But for this, our g of x is any constant, so we'll have this process. Thank you very much for watching.